Okay, T and pi equivalent networks. Okay, it is very convenient for us to replace a transformer by the equivalent network which is having pi or T. Okay, pi or T means so my transformers look like this. This is pi, this is T. Okay, these kind of networks can be drawn as an equivalent circuit for this transformers. Okay, let us derive the equivalent circuit for linear transformer. So let us write the linear transformer to draw T equivalent. Okay, let us use a linear transformer and we are going to draw the T equivalent circuit. Okay, let us consider a linear transformer. This is a linear transformer circuit. We have j omega L1. Okay, this can be j omega m. Okay, not m, just j omega m. And this is j omega L2. V1 is the voltage across the primary winding and V2 is the voltage across the secondary side. Okay, now we need to apply KVL for the mesh 1 and mesh 2. Okay, so in the primary side we have current I1, in the secondary side we have current I2. Okay, so it is very simple. We can apply KVL here. We will get minus. Okay, just zoom this. So we will get minus V1, okay, plus j omega L1 I1, which is self-induced voltage, and there is a mutually induced voltage due to the current I2. The current I2 is entering the dot here, so the generator voltage positive will be here and negative will be here. And what will be the generator voltage? J omega m multiplied by I2. And now check the direction of I1. I1 is entering positive, leaving negative. So it obeys the passive sign convention. So plus j omega m I2 equal to 0. So minus V1 we got j omega L1 I1 and j omega m I2 equal to 0. So I can rearrange it. Okay, rearrange it and consider it as equation number 1. I just took V1 to other side. Apply KVL at mesh 2. While applying KVL at mesh 2, I2 is in the anti-clockwise direction. So we have minus V2. Okay, we have minus V2. So plus j omega L2 I2. Okay, which is self-induced voltage. So j omega L2 multiplied by I2. Okay, I2 is the current flowing through this inductor. Okay, so we can directly multiply the current and the impedance j omega L2. Okay, so I will be getting I2. Okay, and then there will be a mutually induced voltage due to the current I1 flowing through this. Current I1 is entering the dot, so generator voltage positive will be here and negative will be at the undoubted terminal. Negative will be at the undoubted terminal. So if I see the current I2 is entering positive and leaving negative. And what is the voltage appearing here? J omega m multiplied by I1. Okay, it is based on the current I1. And it obeys the passive sign convention, so we will get plus j omega m I1 equal to 0. If I rearrange it, I will be getting the equation like this: j omega m I1 plus j omega L2 I2 equal to V2. So I can write this equation 1 and equation 2 in the matrix form. So V1 and V2 will be on the left hand side. Okay, equal to coefficient of I1, coefficient of I2, j omega L1, j omega m, j omega L1, j omega m. Here coefficient of I1 is j omega m, coefficient of I2 is j omega L2 multiplied by I1 I2. So this is what the matrix we are going to get for these two equations. Now consider a T or Y network. Okay, now consider a T or Y network. So I am considering that here. So I am considering a T or Y network. I am considering LA, LB and LC. In that we don't have any dots and all. It is just a coil. Okay, we have three coils, LA, LB and LC. It is an equivalent network which I can draw for the linear transformer. T equivalent network or Y equivalent network, whatever I can call. So in order to do that, I need to write in a matrix form of the same of this T network. Okay, in the similar way. Then only I can compare the two matrices and represent what is LA in terms of L1 and M, what is LB in terms of L1, L2 and M, and what is LC in terms of L1, L2 and M. Okay, so I need to equate. I need to write the equivalent value so that I can draw the T equivalent network. Okay, so let us consider the T equivalent network. This is a standard diagram. Okay, so we have current I1, voltage V1 at the primary side, we have LA, LB, LC, and voltage V2 at the secondary side, and I2. Okay, so now we can apply KVL here in the mesh 1. So minus V1 plus j omega LA into I1 plus j omega LC. This is okay. This can be written as j omega LA. This can be written as j omega LC. This can be written as j omega LB. If I simply write LA, LB, LC, it will be considered as a time domain. Okay, so in the frequency domain, I need to represent the inductance value like this: j omega L. Okay, so j omega LA, j omega LB, j omega LC. These are all the values. So j omega LA times I1. Okay, and then what is the current flowing here? I1 minus, sorry, I1 plus I2. So see the direction of current I1, direction of current I2. Okay, this is node A, and this is the current I need. Okay, I is going downwards, so I1 plus I2 minus I equal to 0, so I equal to I1 plus I2. So both I1 and I2 are in going towards the node. Okay, so there will be total current I1 and I2 which is flowing through LC. So j omega LC multiplied by I1 plus I2. That is why I1 plus I2 is written here. Okay, so what I have done, I just applied the KCL at this node. Consider the current flowing here is in the downward direction I. Okay, so we got j omega LC I1 plus I2 equal to 0. So I can rearrange it and be getting equation like this. So I'll erase this so that I can write for the loop 2. Okay, so this need to be represented as j omega LB, this is j omega LC, this is j omega LA. So here the current is in anti-clockwise direction, so minus V2 j omega LB into I2. Here the current is I1 plus I2 as we already discussed, I1 plus I2, and the value is j omega LC. Okay, so plus j omega LC I2, I1 plus I2 equal to 0. So I can rearrange and write the equation number 5. Now I can write this two equation in matrix form. Actually it is not 0, it has to be V2. So we have V2 on the left hand side, this can be taken to the right hand side. Okay, this has to be V2. So we got these two equations. Okay, we got these two equations. Now we can write this equation in matrix form. So j omega LA plus LC, okay, which is the coefficient of I1, j omega LC coefficient of I2, j omega LC coefficient of I1. Here j omega LB plus LC is the coefficient of I2, multiplied by I1 I2 equal to V1 V2. So both the right hand sides are same. Both the matrix look in the similar way. So it is possible for me to compare these two matrices. Okay, so we have matrix 3 and matrix 8. Both we are comparing. So this coefficient I will compare first. J omega LA plus LC is equal to what? J omega L1. So j omega LA plus LC is equal to j omega L1. So L1 can be written as this j omega and this j omega will get cancelled. LA plus LC I will get. Next j omega LC, this will be compared with j omega M. Okay, so j omega LC equal to j omega M. So LC can be written as M. So I can substitute here. So L1 equal to LA plus M. L1 can be written as LA plus M. Okay, this is what we are written here. Next, this need to be compared. J omega LB plus LC. So j omega LB plus LC is equal to what? J omega L2. J omega L2. Just equate it as it is. So I can cancel this j omega and this j omega. We'll get L2 equal to LB plus LC. We know LC is equal to M. So L2 equal to LB plus M. Okay, so LB is equal to L2 minus M. This is the final answer. So we got what is LA, what is LB, and what is LC. Okay, by knowing all the three values, it is easy for me to draw the equivalent network. See, if you see LA, LB, LC, it is written in terms of L1, L2 and M. So this L1, L2 and M is already we have. Okay, we have all these three values, L1, L2, M values are already known. So you can simply substitute and find what is LA, LB and LC, and directly we can use this standard diagram for the T network. The T network standard diagram is here. We just substitute what is LA, what is LB and what is LC to write to draw the T equivalent. Okay, to draw the T equivalent for what? For the linear transformer. Thank you.